Compressible flow tutorial question number 26. Air flows from a reservoir maintained at 25 degrees Celsius and 500 kilopascal absolute. It flows through a nozzle with throat and exit diameter of 50 millimeters and 100 millimeters respectively. What receiver pressure is necessary to locate a normal shock wave at a location where the diameter is 80 millimeters? Also determine the velocity before the shock and at the exit. From this question, we can draw a diagram like this. We have a reservoir here, and we assume that it has a high pressure, but the velocity is zero. So we could say that the pressure here is the stagnation pressure. Then we have throat here, and we imagine the Mach number at throat is equal to 1. The diameter is 50 millimeters. And then we have an exit here with diameter 100 millimeters. However, the shock wave did not occur after the exit area here, but the shock wave occurred at diameter of 80 millimeters here. Now, if we draw the flow, we could say that it starts from 0 here, the stagnation here, through the throat with Mach number 1 here and go to point number 1. Here, the Mach number should be in supersonic condition. Then the shock wave occur, and then it will reduce the Mach number. So the Mach number at point number 2 here must less than 1. And then it continue flows to point number 3. The pressure at here with certain values, and then it will reduce to the pressure at atmospheric. So in this question, we have receiver pressure. Receiver pressure means pressure that occur at the exit. From isentropic flow, we could see the table. When Mach number equal to 1, we could get ratio P over P naught is 0.5283 and T over T naught is 0.8333 as stated here. Means that we could calculate the pressure at throat as this one, because we already know the pressure of stagnation, P naught and PT, which is equal to the pressure at the reservoir and temperature at the reservoir. From this calculation, we could get that pressure at throat is equal to 264.15 kilopascal absolute and temperature at throat is 248.3 Kelvin. Now we could calculate the area ratio between A1 and A star. A star here is the cross-section area at the throat, and A1 here is cross-section area just before the shock wave, because we are aiming to calculate properties about shock wave that occur at diameter 80 millimeters. So we use diameter of A1 is 0.08 meters and diameter of throat is given here as 0.05 meters. So we could get the area ratio A1 over A star here is equal to 2.56. From isentropic flow table, we could get that for area ratio 2.56, we could get M1 is equal to 2.47. Here, you might have possibilities to have two values. So please take the supersonic value, because we sure that point 1 here is point before the shock wave, and at this point the Mach number must greater than 1. So we took M1 as 2.47. We also could calculate the pressure before the shock wave by using the isentropic flow equation of P1 over PT like this. I hope you still remember this equation. So we substitute the value of Mach number at throat is equal to 1 and Mach number at point 1 is equal to 2.47 as we calculated previously. We use value of K equal 1.4 because the medium here is an air. The ratio P1 over Pt is equal to 0.11608, and then we could calculate the pressure P1 here by multiplying 0.11 with 264.15, and we get pressure at point number 1 here is 30.66 kilopascal absolute. We also could calculate the velocity before the shock wave by using this equation, the temperature ratio in isentropic flow. We substitute all the values here. We could get the ratio of T1 and Tt is equal to 0.5404. Then we could calculate the value of T1 and we get it is equal to 134.2 Kelvin. We could calculate the velocity at point number 1 by using this equation, and it is equal to 573.6 meter per second. Then from this, we could get information from normal shock wave table as like this. M1 is 2.47, M2 0.5159, P2 over P1 is 6.95, and T2 over T1 equal 2.108. Here is the example of the normal shock wave flow, and we don't have 2.47 in this table. What you need to do is you need to do the interpolation calculation to get the exact value of M2, P2 over P1, T2 over T1, and so on and so forth. We could calculate the pressure after the shock wave by using this ratio, and we get P2 is equal to 213.1 kilopascal absolute, and temperature after the shock wave by using the ratio here, and T2 is equal to 282.9 Kelvin. Until this stage, we know the Mach number and pressure at point number 2. However, we do not know the Mach number and pressure at exit. So we cannot use isentropic flow equation to calculate the pressure at exit area. We could use the value of the stagnation pressure from the table. So in this question, I would like to show you how to use the column of PO2 over PO1 here. First, you need to understand what is the meaning of PO2 over PO1 here. PO here, the knot here, the 0 here show the stagnation point, and P2 and 1 here showing the point at number 1 and number 2 here. So mean PO2 means stagnation point at point number 2, which is point after the shock wave, and PO1 is the stagnation pressure at point number 1, where it is a point before the shock wave occur. So this is the meaning of PO2 over PO1. So what is this? What you need to understand about the stagnation at point number 1 and number 2 here? We imagine that if the flow at point number 1, we stop it immediately, so it's become a stagnation point. So what is the pressure on that time? That is the meaning of stagnation point at point number 1. In reality, this point will keep flowing. So it will not stop for a moment and then create shock wave. So we just imagine what happens if flow at point number 1, we're going to stop it, and what is the increment of that pressure. To calculate this one, we see again from the normal shock wave table, if M2 is equal to 0.5159, so we see at this column, so we search for 0.5159, so we don't have that number, so the nearest one is 5169, so mean you need to calculate over here the interpolation, and then you could get the PO2 over PO1 ratio. So between this number, and you need to calculate it precisely, you will get 0.5112. So we could calculate the stagnation pressure at point number 2 is equal to 0.5112 times 500, and you will get it is equal to 255.6 kilopascal absolute. So here, the stagnation at point number 1 here is equal to the pressure at the reservoir, because pressure at the reservoir, it has no velocity, means it is a stagnation condition. So we could assume that pressure at this moment is equal to the stagnation pressure at any point between 0, throat, and number 1. So stagnation pressure at point number 1 here is equal to pressure at the reservoir. So we take 500 kilopascal as the stagnation pressure at point number 1. Isentropic flow occurs from point 2 immediately after the shock wave to the exit for M2 equals 0.5159. From the isentropic flow table, we could get A2 over A star is equal 1.314. You could confirm it with your isentropic table. If area at exit AE, we could calculate as AE over A star is equal to A2 over A star times AE over A2. So we could cancel the value of A2 here. Finally, we could get AE over A star. So we already know the value of A2 over A star and AE over A2. We substitute the value. A2 over A star is 1.314 and AE over A2 is 0, can be calculated as this one. Exit has diameter of 0.1 meter and A2 is a location where the shock wave occur. It is 0.08 meter. So in this calculation, actually you need to calculate by using pi d square over 4, because pi and 4 is a constant and we could cancel it. So we could simplify the calculation of area ratio for AE and A2 here by only using its diameter. Please be careful about this one. And then we could get that the area ratio of AE exit over A star throat is equal to 2.053. Then we could calculate the pressure at exit. The Mach number and pressure ratio corresponding to this area ratio, 2.053, from the isentropic flow table can be determined as 0.298. Here, you may have two readings, so we need to find subsonic value because it is happened at the exit after the shock wave. Mach number must less than 1. So from the table, we get that Mach number at exit is 0.298, so we could calculate P over P naught is equal to PE over P stagnation at number 2 is equal to 0.940. So we could calculate the pressure at exit by multiplying 0.940 with the stagnation pressure at point number 2 here. So we get the answer for pressure at exit is equal to 240.3 kilopascal absolute. Then we could calculate the temperature at exit. So we know this equation. So we could simplify that T2 over T exit is equal to P2 over P exit by the power of K minus 1 over K. And we could get temperature at exit is equal to 292.8 Kelvin. Then the velocity at exit can be calculated by using this equation, Mach number times speed of sound. We substitute all the values. The K is 1.4, the gas constant is 287, and temperature at exit is already calculated here. So we get velocity at exit is equal to 102.2 meter per second.